there's one more kind of ANOVA that I want to talk about. Sometimes it's called a within subjects ANOVA. Or repeated measures ANOVA. And so it's a lot like a paired sample t-test in the way that the data is structured. So what we're going to do is work with another example where people have drank caffeinated or decaffeinated coffee, and then we measure their alertness. And so here we're going to set up our data like this. This is our participant, and this is when the participant drank decaf. Here's when they drank caffeinated coffee. This is the drink variable. We'll just have two participants to keep the math simple here. And we'll say when this person A, drank decaffeinated coffee, their alertness measure was 4, and it was 6 when they drank caffeine. And for the other person, it was also 4 when they drank decaffeinated coffee, and 10 when they drank the caffeinated coffee. Here, just like with a paired sample t-test, each person's got two different measures. Or this could have been, for example, like a couple where this is the husband and this is the wife, and they would have been paired that way. But the way it's set up, you could consider this more of a repeated measures kind of setup. Remember, with a paired samples t-test, we calculated the different scores, and then we did a one sample t-test on those different scores, with the null hypothesis being that there's no difference. Well, within subjects ANOVAs, we're not going to do that. In fact, we're going to do an ANOVA like we are familiar with, except for we're going to treat the participants' data a little bit differently. In fact, what we're going to do is we're going to treat participants as a factor, or like as a variable, but we're going to remove their sums of squares and degrees of freedom from the mean square within. So our F statistic has this on the bottom, so our bottom is going to be extra small because we're going to get rid of any of the variability that's consistent between our participants. Just by treating it as if we'll calculate it sums of squares and degrees of freedom just the same way we will with the drink. And we'll go through that in a second. That's why I wanted to do a really simple data set, because I want to show you how the math works. This simple demonstration of within subjects ANOVAs, the easiest way to do it is with the sums of squares approach. And so the first thing we're going to need to do is calculate our marginal means. So 4 plus 4 is 8 divided by 2, so the marginal mean here is 4. The marginal mean there is 16 divided by 2 is 8. The marginal mean over here is going to be 5, and the marginal mean here, 14, is 7. And then the overall mean is going to be 6, and you can calculate that as the average of these two or the average of these two. So the first thing we'll do is calculate the sums of squares total. And remember, this ignores any kind of grouping. So for this, we're going to take these 4 scores, calculate their sums of squares with respect to the grand mean. So here we have 4 minus 6 squared plus 4 minus 6 squared plus 6 minus 6 squared plus 10 minus 6 squared, negative 2 squared plus negative 2 squared plus 0 squared plus 4 squared, 4 plus 4 plus 0 plus 16, and that's going to be 24. So our sums of squares total is going to be 24. So remember, just like with the other ANOVAs we talked about, all of the sums of squares that exist across all of the different ways of breaking down the data, those are all going to add to the sums of squares total. So this is the total sums of squares available to work with. All right, next we'll calculate the sums of squares for the drink variable, and this is exactly like it was for between groups ANOVA. So we'll use the marginal means and compare them to the grand mean, and for each marginal mean you do it for one time for each data point in there. So 4 minus 6 plus 4 minus 6, right? And that's because there's 2 here. Then we do 8 minus 6 squared 2 times, once for each of these two. All right, this is negative 2 squared plus negative 2 squared plus 2 squared plus 2 squared, 4 times 4, so that's going to be 16. So our sums of squares for the drink independent variable is going to be 16. Now we'll calculate the sums of squares for our participants. This is the same approach we just used for drink, but we're going to do it this way. So participant A's average is 5. So 5 minus the grand mean. And we had 2 measures for that person. And then person 2 had a mean of 7. And so this is the difference between our participants that's unrelated to the drink. So this person tended to have a little bit lower I guess alertness compared to this person. And for our Anova, we're interested in the drink difference rather than the individual differences. And so we're going to exclude these sums of squares and their degrees of freedom from our error variance, our mean square within. Okay, so for the person B, 7 minus 6 squared plus 7 minus 6 again squared. All right, so this is negative 1 squared will be 1. Negative 1 squared is 1. 1 squared is 1. 1 squared is 1. So these are all going to equal 4. So our sums of squares participant is going to be 4 sums of squares. All right, so I'll put that here. So the only sums of squares left to calculate are the sums of squares within. Remember, this isn't within participants. This is within the conditions. And now for this, we're not going to calculate it from the raw data. Instead, what we're going to do is we're going to take the total sums of squares and subtract the sums of squares from the independent variable. And then from whatever's left over, we'll subtract the sums of squares from our participants. And whatever sums of squares remains, those are the sums of squares within that we'll use. So sums of squares total is 24 minus 16 minus 4. So this is 8 minus 4, 4. So our sums of squares within is going to be 4 in this case. All right, so I've got the source table set up here, so we'll start filling it in. So first we want the sums of squares for our independent variable. So that's 16. For participants it was 4, or within it's 4. Sometimes this is called error because it's just the variation that we're not interested in. And sums of squares total goes down here. And now we got to figure out our degrees of freedom. So for drink, that's pretty easy because for drink there was 2 means. So there's 2 groups, so the degrees of freedom, as usual, is n minus 1. And n in this case refers to the number of groups, just like it did with all of our previous ANOVAs. So 2 minus 1 is 1. Degrees of freedom for drink is going to be 1. Their degrees of freedom for participants is going to be calculated the same way. There's 2 participants, there was 2 means. So the number refers to the number of means here, because that's what we use to calculate it. And that's going to be 2 minus 1 is 1. The degrees of freedom within, just like for sums of squares, is going to be whatever's left over after we take the degrees of freedom total and subtract those for these other variables. Our degrees of freedom total is going to be our number of observations minus 1. So n minus 1. And the number of observations in this case is 1, 2, 3, 4. We have 4 independent pieces of information there, minus 1. So our degrees of freedom total is going to be 3. And then our degrees of freedom within is going to be the degrees of freedom total minus the degrees of freedom for drink minus the degrees of freedom for our participants. So that's 3 minus 1 equals 1. So we have 1 degree of freedom there. And as always, all of these have to add up to the total. Next, we can calculate all of our mean square values. Remember, mean square is a variance estimate. For our mean square drink, it's going to be our sums of squares drink divided by our degrees of freedom drink. So 16 divided by 1 is 16. Our degrees of freedom, or our mean square participant, that's our sums of squares for our participant divided by degrees of freedom for participant. 4 divided by 1. 4 divided by 1, so that's going to be 4. And then our mean square within is going to be our sums of squares within divided by our degrees of freedom within. 4 divided by 1, it's also going to be 4. So there's all of our mean squares values. All right, so remember, for this research, we're interested to determine whether or not caffeinated coffee results in more alertness than decaffeinated coffee. So the research that we're doing has a null hypothesis that the alertness of the decaffeinated population is the same as the alertness in the caffeinated population. All right, so what we're hoping to reject this null hypothesis, and that is going to be related to this F statistic here. So we'll want to calculate the F for drink, the F statistic for drink. And that's going to be the mean square drink divided by the mean square within, which is exactly what it was before we had these participants involved. And it's 16 divided by 4. So we get a F of 4 for drink. So we need to decide whether or not we can reject this null hypothesis based on this F statistic. So I look in my F table, and I need the degrees of freedom in the denominator. So there was 1 for the mean square within, and then for the numerator, it also had 1 degree of freedom. So that's not the kind of situation you'd usually have in real research, but for this really simple example, we hardly have any participants. And the F critical for a 1 and 1 degrees of freedom for alpha 0.05 is 162. So we would have had a huge F given these very few observations to be able to reject the null hypothesis. Our F statistic is not even close to being more extreme than our F critical, so we're going to fail to reject the null hypothesis in this case. But really what I wanted to do was introduce how the logic of a within subjects ANOVA works. Notice you could calculate the F statistic for your participant, but that's not anything that's really of interest to us because that's not what our research is about. And a big advantage to doing a within subjects design is you actually end up with more statistical power by getting to remove all of this participant sums of squares well, it's really the sums of squares you want to get rid of from the within. And so that ends up increasing your statistical power if there really is an effect in the world. So that's an advantage of using a within subjects design so that you can use a within subjects ANOVA.